Hello everyone and welcome to STEMfest 2015. My name is Bradley Layton and I'm a professor at the University of Montana where I direct the Energy Technology program. Before we get started, I want to thank you for spending time with me, Governor Bullock, and the fine folks at the Inspired Classroom and an organization known as We Are Montana in the Classroom, who place University of Montana faculty members, graduate students, and professionals in K-12 classrooms statewide to inspire them about higher education and career pathways. Today, with the technology provided by VisionNet, we are able to fulfill this mission. This event is part of a national initiative called STEM Career Accelerator Day, being hosted by STEM Connector. You can find more about their organization at stemconnector.org. My first connection with STEM Connector came through as a result of a National Science Foundation grant I received through their Advanced Technology Education Division to enhance the educational opportunities for my energy technology students, a few of whom you see behind me, to strengthen our relationship with the Blackfeet Community College, to build connections with renewable energy technology companies, and to build connections with high school students around Montana and across the United States. You probably already know this, but the presentation you're about to take part in is a minds-on activity. So get comfortable in your seat, take a deep breath, and get ready to meet and interact with some of Montana's leaders in science, technology, engineering, and mathematics. Now, I'll hand it over to Governor Bullock, who would like to share with you his vision for the future of STEM education in Big Sky country.
Hi everyone, I'm Governor Steve Bullock, and I'd like to thank you for being a part of the first ever Montana STEMfest and showing an interest in a career in the fields of science, technology, engineering, and math. These are some of the fastest growing career fields in the nation. In fact, over the next decade, Montana is expected to need more than 2,000 new workers a year with skills specific to these fields. And these are good paying jobs in careers such as engineering, research and technology, architecture, and health sciences. I've been working hard to ensure that students like you have access and support to succeed, which is why we've created the Governor's STEM Scholarship Program to provide financial aid to students pursuing one of these careers. We've also launched the Montana STEM Mentors Initiative to encourage more girls to pursue a career in these fields. You all will determine what the future of Montana looks like, and your participation today means that we will have a bright one. Thanks so much for being here and have a great time.
Sure. My name's Kelly Barton, and I work for a company called Rivertop Renewables as a senior scientist. And I actually live in Hamilton, Montana, and the reason I like living down there, I feel it's the best of both worlds. There's a really vibrant community, but still you're really close to being in the outdoors and can get away very simply. And STEM impacts my life every day because I work as a research chemist.
Fantastic. Brian?
And my name is Brian Kerns. I'm an engineer on the University of Montana, and I also teach alternative fuels and bioenergy at Missoula College. And I live in Missoula, and I love Missoula and Montana for 4 seasons. I lived for a good part of my career in the southern states, Oklahoma and Texas, that didn't have 4 seasons, and it feels really good to feel fall as fall should be felt. And like Dr. Barton, I use STEM every minute of every day. I'm an engineer and I use math, science, technology, engineering all the time.
So I'm going to kind of turn it on its head today, and I'm going to tell you a little bit about green chemistry under the big sky. And so green chemistry is really the way that the chemistry field is moving. And the easiest way I can think of as explaining it is this is the way that nature does chemistry. There's no waste. It's not creating anything that's damaging to the environment. The easiest way to think about it is like photosynthesis. It uses the water, the minerals, the CO2 in the air to make everything that the plant needs with sunlight and giving off oxygen that other living organisms need. There's nothing damaging to the environment about photosynthesis. And as chemists, we need to start thinking that we're doing things that are not damaging to the environment. And so there are 12 principles of green chemistry, and I just want you to focus on a few of them as I tell you about what Rivertop Renewables does. And they are, can you make chemicals in a safe, non-hazardous way where you're not creating a lot of waste? But also, are these chemicals biodegradable? Are they safer than the chemicals that you make today? And are they coming from sources that are renewable, that we're not using up non-renewable resources that we have in the world? And so, a little bit about the history of Rivertop. It was started by a really great chemist named Don Kiley, who wanted to make polymers that were renewable and biodegradable from glucose using a molecule called glucaric acid. So how many of you know what I mean when I say glucose? Do any of you know what glucose is? Okay, how many of you know what starch is, or cellulose? Anyone? Okay, starch and cellulose are basically made up of glucose molecules. And so he wanted to use something that we have naturally in the world and make chemicals from it that could replace things like nylon and Teflon and PVC. Okay? The problem was glucaric acid is very expensive. So what he started to do was figure out a way to take glucose and make glucaric acid so he could make the polymers that he wanted to make. And so this is not new chemistry. What I'm about to tell you about the chemistry has been done since the late 1800s. Okay, so this is stuff that's been going on for years. But what Rivertop has been able to do is make it renewable and safe for the environment. Okay, so when you look at this screen over here, you'll see the Rivertop process and then the conventional process. Okay, the conventional process puts all of this brown gas called NOx into the air. Okay. Recently, Volkswagen has been in the news for evading emission standards. This is what they're putting into the environment. Okay, this is really bad. But this is how it was conventionally done. What Rivertop has done has added oxygen to the system, so we no longer create that toxic gas. We're no longer putting anything into the air, into the environment that we don't want to breathe. Okay? And what's nice about this is we're not creating anything new. We're just modifying the old. New chemistry takes a very long time to develop. But here, we're just modernizing something. And so, Rivertop has a few things that it can do. I talked to you about glucose, but it can use so many different feedstocks. We can start with corn. We can start with starch. We can start with leftover material after sugar is extracted from sugarcane. And it can all be put into our process to make a whole lot of different chemicals. And these are the chemicals that we can find applications and uses for. They're all biodegradable, they're all safe for the environment, and they'll naturally promote a healthier environment when they enter the system. So there's no longer damaging to the environment. So I want to tell you about a few things that we do. We have a lot of different products that can go in paints, can go in the oil and gas industry, they can be put into foods. But I'm going to tell you about two today that I think are really relatable to what you live every day. One of those is dishwashing detergents, and the other is what's put into de-icing on the roads in the winter. And so why would we want to enter the market for dishwashing detergents? Okay, there's one main reason, and that's called eutrophication. Okay, eutrophication is what happens when nutrients are released into the environment that cause overgrowth of plant life, specifically in lakes and streams. And what happens when you get overgrowth of algae and weeds, you kill off the fish and most of the other living beings within that environment. So you take a beautiful, pristine lake and you end up with one that looks like this, which isn't very interesting and is bad for the plant life and growth. Okay? One of those nutrients is phosphates. And phosphates are commonly found in dish detergents. And our chemicals replace those phosphates. So we prevent the fish from dying. But if I told you we replace bad chemicals, the first thing a consumer is going to want to ask is, well, what does it do for the product? They want something that also is good for the product. And so if you look behind me, and what you'll see here is a series of glasses. Okay, you'll see a clean, unwashed glass and 3 glasses that are by detergents that are on the market. Okay, and you can see they're spotty, they're filmy. One of them actually looks like you put a blue film on a clear glass. Okay, but this is the Rivertop glass. Okay, and so what you can see is it's nice and clear. It definitely doesn't have as much spotting. So we've replaced a bad chemical for the environment and made a product that performs just as well. Okay, so those are things you have to think about. Green products are great, but you still need to have the functionality. And so the next thing I'm going to talk to you a little bit about is corrosion inhibition. Okay, this is a salt brining truck that you can see behind me over here. And the idea is to use less salt on the road. They've commonly just put solid salt on the road. But one of the principles of green chemistry is use the least amount of chemicals as you can. So by brining, making a solution of salt water and spraying that on the roads, you use about 5% less salt, okay? But the problem with it is you often get bridges and trucks that look like this, because now that salt is sticking to the bridges, it's sticking to the trucks, it's sticking to the roadways, and you're creating more corrosion. We have a product that you add to the brine that prevents that corrosion. And so here you can see we do this in the test in the lab, and you can see that what you have over here is on this side, this is the normal salt brine, and this is all the rust. All that red stuff is the rust that happens over time. And you can see down here, there's actually spots where the metal has completely been removed from this test strip. Okay, and we compare the weights before and after and can show the weight loss that happens from here to here. But when you look at the Rivertop, what you see is a 70% less corrosion. And you can see that it almost looks like a brand new washer. Okay, and so you have to be able to show the functionality. And so when you think about everything that I've told you about Rivertop, do we prevent waste? Yeah, we're not putting that noxious gas into the air. We're doing less hazardous chemical synthesis. You know, we don't want to live in a place that looks like China. We're creating safer particles that are biodegradable after use. And we're using renewable feedstocks. We're using leftover corn, sugarcane, and everything to make these products. And so Rivertop actually adheres to all 12 of these green chemical principles, and that's why we feel that we have a really good spot in the environment right now and in the world. And so I want to tell you a bit about what I do and what everyone that does STEM at Rivertop does every day. Okay, so this is a little pie chart based on what the people do every day at Rivertop. So about a quarter of our company do not have STEM degrees. They are the HR people, they are the administrative assistants that we have that run more of the office side of things. But almost 3/4 of our company have STEM degrees. Our CEO has a master's degree in food science, and our starting lab personnel usually have a BS or a BA in a chemistry field. And so they can do a couple of different things, and sorry, this PowerPoint looks a little off, but one of the main parts is doing applications and products, okay? Now this includes lab people who are doing those tests with the dishwasher, but it also includes the business development people, the people who go out and look at customers and find out what they need and what they want and whether or not we can provide that. So they're not just sitting and slaving away in the lab every day. Another big part of the STEM that we have are the design and process manufacturing people. These are our chemical engineers. They're the people who take what we do as chemists in a lab on a very small scale and scale it up to a plant that can make 10 million pounds of product a year. So they're doing all of those, you know, the Legos you talked about earlier, they're putting all of those pieces together and designing our plants and designing the processes that are going to make the 10 million pounds a year. And then we have analytical chemists. They need to make sure we know exactly what's in our product. Anything that goes out into the world, you need to know exactly what's there. We have a couple of students. We always carry undergrad interns, and we currently do have one who's majoring in chemistry at UM, and she's working for us. She works full-time in the summer and then part-time during the school year around her classes. But we also have someone who's doing a very traditional route in a non-traditional way, and he's getting his doctoral degree while working at Rivertop. And then finally, we have what's called the Discovery Group, and that's the group that I work in. And we are basically, when you think of a research and development, we are the research. We are the big R. We're doing products, we're making products, we're looking for that version 2.0 that's bigger and better and more innovative than what we're currently selling on the market. And so that's what we do every day. And so, you know, being in a STEM field doesn't necessarily mean that you're sitting there designing experiments every day. And I think that's what I wanted to get across by showing you this graph. And when you look at these people who have degrees in Rivertop, they have everything from biochemistry to biology to chemical engineering, and anywhere from bachelor's degrees all the way up through doctoral degrees.
So that was an exciting presentation by Dr. Barton. What do you think? I'm a chemical engineer, by the way. I think after I'm done with this, I'll send in an application and see if I can work for Rivertop Renewables. Trying to figure out how best to position myself. So today I wanted to talk about a project that I was lucky enough to get funded for by the the U.S. Department of Agriculture, who does the Forest Service, and it was to make bioenergy out of waste wood. Now, we know about renewable energy. You just heard some renewable chemistry issues. Let's talk a little bit about renewable energy. A lot of people's mind, renewable energy and sustainable energy usually mean the same thing. I don't think they are. Let's back up a little bit. Let's say you wanted to do something with renewable energy and you're sitting in Arizona. What would you use? Sun, maybe? How about if you're in eastern Montana, where, so how about Great Falls? Great Falls, what would you use there for renewable energy? Wind, maybe? Yeah. How about here in western Montana or the Pacific Northwest? What renewable energy do we have an abundance of? We have a lot of wood. So wood is renewable because if you use it, you can regrow, right? So that's what the whole thing of renewable means, is it's replaceable. But sustainable is a different thing, right? If you chop down all your trees and use them all, well, it might be renewable, but it sure ain't sustainable because it's all gone. And and I don't have a slide of it, but sometime if you look at the two countries, they're side by side, of Haiti and Dominican Republic. There's right at the divider line, there's trees on one side and nothing on the other side. So that's an example of what happens when a renewable resource is taken beyond the point of sustainability and is gone. So let me tell you a little bit about my project. This was a pretty interesting gig I had for a few years. I was traveling around the state and did a couple of interesting things. This is a little demonstration I was doing in up in the Patty Creek area with some fourth graders. And this is my rig right there. And what I was doing in Kerns Park, Missoula, was powering a soundstage with waste wood. So I take waste wood and I make electricity from it. And this is another gig I had at the Montana State Fair. It's doing the same thing there. And I don't know if you remember, you just saw an introduction from our current governor, Steve Bullock. Do you remember who the past governor was? Brian Schweitzer, huh? That's him there. And he was really famous, I think more famous because of his, his dog. His dog Jag. And I'm the ugly one there in the, on the other side. So I was talking about waste. So in Montana, anywhere where we have a lot of timber, what happens when you cut trees down is you have what they call wood slash. And you see this pile of material behind me here. And those are trops and limbs and roots and all sorts of stuff from harvesting trees that they can no longer use. And so they pile them up like that, and they wait for a couple of years, and then what happens? You know? They go back and they do this to them. So really, there's a lot of energy in wood, right? We use energy to make campfires, and it was one of our first forms of energy in the world. And really, this is energy that's going up literally in smoke, right? A minute ago, it was useful. There's some material there that can be turned into useful energy, and now it's just going up in smoke, waste heat and waste smoke. So I think a big point of my presentation is turning waste into something useful. Transforming waste into a useful substance, in my case energy. And how do I do that? It's a process called downdraft gasification. I won't get too technical about it, but basically you put wood and air into this big reactor and you heat it up and it starts burning basically. Instead of the smoke going up in the air like you saw over here, I have a fan on this unit and it draws the smoke down through the system. And then there's energy in that smoke, and I use that energy to run my gasifier. Now, like Dr. Barton said earlier, her technology has been is old technology, done in the 1800s, if I remember correctly. This one is too. This was actually done in the 1600s. So they had a way of turning wood into energy back in the 1600s and through a thing called gasification. Now, it was just sort of an unusual process back then. But then in World War II, it was interesting in that Germany and Sweden, they didn't have a lot of access to petroleum like the Allied powers did. So they're looking for other means of powering their vehicles. And this is an old German bus in the 40s, and they're using wood. I don't know if you can see this, but over here, this guy on top there is putting wood in the gasifier, and this bus is running on wood. So again, you can see, I can't get this thing straight here. Over here, there we go. The gasifier is right there. This is another German vehicle. This was a small German Jeep that again was made during World War II. And there's a gasifier on this. I don't know if you can tell, but if you see the hood here, how bulbous it is, and this thing right there is gas. So they're making gas, and the engine is actually in the back. So they're heating up wood here, and the gas is going in the back to power the engine in this car. And here's another one from Sweden. Let me move over here a little bit. And if you can see in the front there, that's a production-made car with a gasifier already built into the front of it there. Again, this is in the 1940s. And here is a German plant where they're making trucks with gasifiers all over the chassis of those trucks. And then here's a more modern version of somebody on a motorcycle. And you can see in the back there his gasifier on the back of his motorbike. And here is another modern example of, I think it's a Volvo car. And you see that trailer there is a gasifier where they're using wood, they're making the gas, and you can see the gas coming up underneath the car and into the front end of the hood to the engine to make that thing run. So again, this is an old concept just being more or less brought up to date. And here's a better shot of my gasifier. You see that this thing here is the gasifier. And I take that wood, it goes through there, and it makes a smoke. The smoke goes down, it goes into a heat exchanger, goes over here into a filter, and then it powers a generator. And it makes about 25 kilowatts of energy and 200,000 BTUs an hour of heat. And how much does that mean? That's about enough energy for 15 to 25 homes, okay? So a little unit like that can power 15 to 25 homes. Now, I was telling you before about using waste. I'm using waste wood. You saw that big pile of slash. That was some of my feedstock for making my gasifier run. This is an island, and you can see some trees in the background there, palm trees. And what comes off of palm trees? Coconuts, huh? So when you crack a coconut, you have coconut hulls, and you see this big pile of coconut hulls here. They had a gasifier over there, so they used something similar to what I had, and they were making energy from waste coconut hulls. Here's another example. This happens to be in California, in a walnut manufacturer. And when you have walnuts and you crack the walnuts, what are you left with? Shells, right? So you can see here in the back 40, they have a whole bunch of of walnut shells. And this is a gasifier here underneath the this awning here. This is a big gasifier. So they're using the waste walnut shells over here, putting it in here, and they're making power for this this walnut factory. Now, again, in keeping with the trend of waste, turning waste into useful materials, this, I don't know if everybody knows what this is, but this is what they call an MRE, or a meals ready to eat, and this is what the Army uses all the time for their troops. So you get this packet, and it has all this stuff that you can just eat. I don't know, you can see some peanut butter in here, some kind of beverage powder, coffee, whatever, pretzels. So what happens when the soldier eats all this stuff? You know, he's got all this waste, right? He's got this packaging, he's got plastic spoon, napkins and stuff like that. So what the Army has started doing is collecting all this stuff, making pellets out of it, and they have a gasifier, and they turn this energy, this waste material into energy. So this process is, I call it carbon neutral, because as a tree grows, right, it takes carbon dioxide out of the air, it goes into the tree, and the tree grows. Then when we cut the tree down and we process it, the carbon dioxide goes back into the air. So it's a circle. We're not adding any new carbon dioxide in the air. We're just taking stuff that's currently in the air, putting it into a plant, a tree, and then we put it back up in the air. So we're adding no new carbon dioxide into this process, so it's carbon neutral. And actually, if you think about it, if you use a gasifier like I have, and you make your own energy and heat with it, then you're not using energy and heat that you'd get from your utility. So you're not using electricity, and you're not using natural gas that you'd use for heat. So in that respect, it'd actually be carbon negative, because the electricity that you would have been using is coming from a renewable resource. So I just want you to think about that, is ways to create something useful out of waste, as I've done here with my gasification project. And that's all I have for now. Thank you.
Thank you. How much does it cost to make one of those gasifier things?
So mine cost about $500,000, okay? But that was a big thing on a big truck. But you can buy small ones, or you can make them. People make them. You saw those people making some, putting them on motorcycles and cars. You can make your own, and that costs a whole lot less.
Wonderful question. Do you guys have another question?
I have a question. Do your plants and products have GMOs in them?
So this one for Dr. Barton.
Is this for me?
I think so.
Okay.
Yeah.
No, in fact, we plan to market most of our products in Europe as well as America, and they have really strict standards on whether or not we can use GMO feedstocks. And so for us, most of our feedstocks are not, so that we can use the same product both in America and in Europe.
Yeah, I have a question about the gasifier. First of all, we couldn't really hear your answer because our speaker was breaking up about what the cost is to create one of those. And I was also wondering, why is this not more widely used? Is it because it's cost prohibitive, or what's the reason that it's not more widely used?
Yeah, pretty much two reasons. One is pretty cost prohibitive. The gasifier, can you hear me okay now? The gasifier that you saw there cost $500,000. Okay, so that's a lot of money. You don't have to spend that much on it. You can buy these small kits for one house that are like, I don't know, $10,000 or something like that. So about the price of maybe air conditioning units and a furnace. And the reason that a lot of people aren't doing it is, for that one reason, is that it's more expensive. Plus, our energy is so cheap here. And when you look at, can you buy and use gasifiers versus using oil or electricity that costs, gasoline costs, let's get them down, right? It's $2.50 or something like that now. And our electricity is under 10 cents. So places where they do work very well are like islands. I showed you a picture of, that was the Philippines actually. So islands that don't have their own natural resources, or Alaska, it's not an island, but there's no natural resource. Well, actually there is a lot of resources up there, but they're pumping it all down to here. But a lot of remote places don't have their, local forms of energy. So like in islands, they have to boat diesel over to it. So those things are very, very expensive. So instead of costing 10 cents per kilowatt hour, they cost more like $1.60. Those are places. And in Hawaii, Hawaii's using some gasifiers right now.
Great question.
So in the zombie apocalypse, Yeah, I have one more question. When the zombie apocalypse comes, where do you live? Because I'm pretty sure I want to be at your house.
Well, you want to live in Missoula because besides my gasifier, we also have the zombie tool manufacturer here. So you'll need a lot of swords to kill them.
Wonderful.
Oh, thank you, Columbia Falls. All right, Sentinel, what do you guys think? Should we have the Columbia Falls guys come down to live with us?
Gasifier harder than my mixtape.
Say that one more time.
Here, I got it.
Okay, yeah, we got one in the back. Stand up so they can see you.
Alright, so with the gasification, is it truly burning it, or is it turning it into gas that can then combust? Like, how does that process work, or is it just the heat and stuff that...
You've been studying your math, haven't you? Your science. Yeah, exactly. Yeah, it's called incomplete combustion. So you don't put a lot of oxygen in there. You need oxygen to combust. Instead, we starve the oxygen. There's a little bit that goes in there, but we basically starve it. So the gas has a lot of combustibles in it. What it has in there has hydrogen. It has carbon monoxide. That's the poisonous stuff, right? But carbon monoxide still burns. Has a little bit of methane. Then also has some CO2 and nitrogen. Good question.
Thank you.
Help me in thanking both Dr. Barton and Brian Kerns for presenting with us today. So thank you guys so very much.